This is an overview of the anatomy of the ear. As we know, the human ear is extraordinary. It can analyse intensities over 12 orders of magnitude with a frequency range of 20 Hz to 20 kHz. To understand how this works a little bit better, we'll break the ear down into 3 sections: the outer ear, the middle ear, and the inner ear. The outer ear, or ear canal, can be thought of as a half-closed pipe. The middle ear contains a mechanical mechanism that circumvents a major loss in intensity that would occur if the external medium air was directly coupled to the inner ear's fluid, and the inner ear provides us the frequency analysis that is then encoded in electronic signals that is then sent to the brain. Sound waves are collected by the outer ear and are funneled by the pinna, here, into the ear or auditory canal. The shape and size of the pinna, which is the skin and cartilage that we normally call the ear on the outside of our heads, captures more sound and helps amplify human hearing by a factor of 2 to 3. This is a very important aspect of the ear. At the end of the auditory canal, the sound waves interact with the eardrum or the tympanic membrane, causing it to vibrate. The tympanic membrane can be considered a circular stiff membrane undergoing simple harmonic motion. The auditory canal can be considered to be a tube with one end opened and one end closed, which has got a natural frequency as a result of harmonics and standing waves formed by the sound waves in the ear canal. Let's examine this in a little more detail. Auditory canal harmonics. So if we model the auditory canal, which is, if you remember, the tube leading to the eardrum, as a tube with one end open that's about 2.5 centimeters long, what is the first harmonic frequency, and is this significant? So let's draw a diagram. This is what it looked like in the previous picture. Here we had a tube with the tympanic membrane at the end here and a length of 2.5 centimeters long. Let's draw this a little bit bigger so we can draw the harmonics involved in this system. You remember, we have a node at the fixed end and an antinode at the open end. The fundamental frequency, or first harmonic for this system, can be seen easily from this diagram. Lambda 1, the fundamental wavelength, is 4 times the length L. As L equals 2.5 centimeters, or 0.025 meters, lambda 1 equals 0.1 meters. Now we can use the wave equation, V equals F lambda. We can rearrange that to find F, our frequency, which is what the question asks for. What is the first harmonic frequency? F equals V on lambda. And we know V is the velocity of the wave. The wave we're talking about here, of course, is sound. And the speed of sound is 343 meters per second. This is at ambient temperature. So our frequency equals 343 divided by 0.1 equals 3,430 Hz, or 3.4 kilohertz. What is the significance of this result? Well, you might remember when we were talking about loudness that the sensitivity peaked around 3 to 5 kilohertz. This is exactly why it peaked, because of this harmonic that's set up in the auditory canal. Interestingly, this is also very important for understanding human speech. Note that this can also be done using the equation Fn equals Vn on 4L. And if we calculate that out, you can see we get the same answer.